All right, now after we kind of established these mathematical preliminaries and talked about big O, big theta, how to think about best case, how to think about worst case, we moved on and started talking about various kinds of algorithm design methodologies. And the first one we looked at was divide and conquer. Divide and conquer is a general form of thinking about solving problems. Typically you use this when you can decompose your problem into non-overlapping chunks. As long as the chunks don't overlap and you can compose a solution to the overall problem out of solutions to the chunks, you're in really good shape for a divide and conquer, provided that you can make the chunks relatively similar in size. So here's the divide and conquer concept. First, you break your problem into, into chunks of size n divided by b. Chunks of size n over b, where n is the original size of your problem. Now you recursively go and solve a of those chunks. A of the chunks. And then you take the solutions from the recursion and you combine them back together in some way to solve the original problem. So combine solutions from recursion to solve the original problem. Okay, so let's see what we have here. So we've just broken the problem into chunks of size n divided by b, and then we're recursively solving these things. So this gives us, to solve the overall problem, in other words, to solve a problem of size n, this means we have to solve a problems of size n over b. And this piece here and this piece here collectively cost some overhead amount, some time to do this breaking and this recombining. So they collectively cost f of n in time overhead. All right, and so then that f of n gets rolled into the divide and conquer recurrence relation right here. Okay, so in the major lecture videos, I described a very specific divide and conquer theorem, and it's called the master theorem. And it had this very detailed description of how you kind of parse the divide and conquer recurrence to get the answer. I'm going to give a simplified version of it in this video. So to find the actual version, go back to my older videos that had the divide and conquer recurrence relation and the master theorem. But here, we're just going to give the simplified version, and this works on a special case of the master theorem. Works on the case where I can specifically say the time complexity of the f of n and its polynomial. All right, so here's the master theorem. And I want to make sure that it's clear. This is the simplified version. Okay, so suppose that f of n, and this is the simplification, is that we're assuming a specific form of f of n. So if f of n is polynomial with a time complexity of big theta of n to the d, so d is the order of polynomial that we're looking at here, then we have the following. Then there's three cases. So t of n is big theta of n to the d if b to the d is greater than a. All right, so this is the case if d is relatively large in this sense, in the particular sense expressed by this inequality. And if d is large, that means the overhead is dominating things. So this is the overhead dominant case. Oops. Overhead dominant case. All right. Now, if we go down a bit, The next case is that the overhead and the recursion is somehow balanced. So this gives us n to the d log log a. So log b of a if you want to be very specific. And this is if b to the d equals a. And so this is what I called the balanced case. Right? The algorithm is being dominated neither by recursion base cases down at the bottom of the recursion tree, nor is it being dominated by overhead that's being executed as you work your way through the recursion tree. And then last, we have this one. It could be n to the log base b of a, and this is if b to the d is smaller than a. And this is the recursion dominant case. You can think of this as recursion dominant, or you can think of this as like most of the work is being done executing base cases of your recurrence relation. Okay, so this is our simplified version of the master theorem. And so we can use this to solve recurrence relations, right? So we can say, suppose I've got a recurrence relation that looks something like this. So here's my example. Suppose, let's see, t of n equals 5t of n over 2 plus n, just plus n, right? So let's do this. So a is 5, b is 2. Let's see, b to the d, to the power of d, is 32. So this is 2 to the 5th. Sorry, not 2 to the 5th. This is, I haven't even written down d yet. I'm jumping way ahead. So d here is 1, right? This is, the overhead term is n to the power of 1. So d is 1. So b to the d is 2 to the power of 1. And that's less than 5, which is a. So b to the d is less than a. And so we are recursion dominant, right? We're in this case here. If we're recursion dominant, then t of n is big theta of n to the log base b of a. So n to the log base 2 of 5, whatever that is, something slightly more than 2. All right, so that's one possibility. And so, you know, what you see here is that the parameters that drive your recursion show up in the the total complexity. So this 5 has to do with your a, and this 2 has to do with your b, and they both appear in this expression, right? And so right now, tuning your recursion would you know, if you could somehow reduce that 5 to a 4 for some reason, that's usually not possible, but suppose you could, that would improve your algorithm. But if you tinker with this, like if you take your overhead term and you optimize it somehow, that's not going to make a difference in the asymptotic complexity of your algorithm. So that's one of the takeaways of the master theorem, is you're either in the overhead dominant regime or you're in the recursion dominant regime, in most cases. And if you're in one or the other, then you have to be aware of where optimization helps you. You can essentially, I mean, this is like crude, but in an asymptotic sense, you can afford to be sloppy with your overhead in this particular case, right? Let's think about a couple algorithms that we talked about using divide and conquer. So one is merge sort. This is very classic. So recall, what does merge sort do? Well, merge sort says first split in half, then merge sort each half, and then you take your merge function, which takes two sorted arrays and weaves them back together, and you use that to solve the problem. So then combine using merge. All right, so splitting in half means our a is 2. So let me color this differently here. So our a is 2. When we merge sort each half, what we're doing is we're saying this is t of n over 2 times 2. And b equals 2 there as well. And then when you combine using merge is a linear time algorithm, and you can reason through that pretty easily yourself. You should just, as a general note, you should understand what the merge function is doing and how it works. It should not be difficult to reproduce. Remember on the midterm in fall 2022, I asked you to know how the merge function worked, and that caused some problems. So make sure that you understand how the components of these algorithms work. And so then down here, that means that our d is 1, okay, because f of n is just big theta of n. All right, and so merge sort then, now that we have all those pieces, we know our a is 2, our b is 2, and so our b and our d is 1, so b to the d is 2. And so this is equal to a, right? And so this puts us in the balanced case. And if we're in the balanced case, then what you get is a log slowdown on the overhead term. So that means our t of n for merge sort is big theta of n log n. And that's the main takeaway from this. So we also talked about quicksort, by the way. Right after we talked about merge sort, we talked about how quicksort almost in some ways does the reverse, right? Rather than spending its effort on the combining the subproblems, it spends its effort on the splitting the subproblems apart. And so understanding why that is relevant is important. Basically what that ends up doing is it makes it so that quicksort has a poorer worst case complexity, because it's very difficult to know how to split the array, a priori without knowing anything else. But on average, it ends up with the same time complexity for reasons that I waved my hands about a little bit in this class. All right, another algorithm we thought about was Strassen's, the Karatsuba algorithm for integer multiplication. And so what this algorithm said is it kind of took this very strange observation that you can multiply two numbers, two-digit numbers, by performing only 3 single-digit multiplications. Okay, so Karatsuba's algorithm says you can multiply, as long as you decompose the numbers cleverly, you can multiply two two-digit numbers by performing 3 one-digit multiplications. All right, and so what we ended up doing is we ended up saying, hey, well, we could generalize this. I can also, just by the rules of algebra, I could also multiply two, let's say, 2 to the k digit numbers. Is that what I want to do? That's fine. By performing 3 2 to the k minus 1 digit mults. Okay, and so this gives us a recursive algorithm where we can take two large numbers, break their digits apart, like separate them out into a highly significant portion and a lowly significant portion, and then multiply those together in a clever way, recombine them in a clever way, and then get the answer we want. And of course, then when we do that multiplication, like if I'm multiplying two 4-digit numbers, that'll generate 3 2-digit multiplications, and so on. Okay, so we can cleverly kind of set these things all up and save ourselves a lot of effort. And so this gives us a recurrence relation of t of n equals 3 times t of n over 2 plus 1. All right? And this thing, well, I guess there actually is no plus 1 if we're just counting multiplications, right? But then this, if we chase this down, this gives us a equals 3, b equals 2, d equals, doesn't matter, right? We can say d equals 0, or it doesn't matter here. And so b to the d is just 1, and that's way less than 3. So we're recursion limited here. And so this tells us that the time complexity of this algorithm is big theta of n to the log base b of a, which is big theta of n to the log base 2 of 3, which is better than the n squared time complexity we would get if we were using the school, just the regular elementary school algorithm. So this has been our quick overview of divide and conquer. Key things to remember are that the master theorem tells you something about where optimizations can help. The master theorem also tells you more generally, even than I've done it right here, how to relate the structure of the recursion and the time complexity of the overhead in order to kind of get the final answer that you're looking for. And you can use it to analyze a bunch of really interesting recursively themed algorithms.